Students, Jai Swaminarayan. I am Professor Urvish Mewada, HOD Electrical Department, Sri Swaminarayan Institute of Technology, Gandhinagar. I am the subject matter of Interconnected Power System subject, which is in the 7th semester Electrical Engineering, and GDU subject code of this subject is 2170901. Students, currently we are discussing the chapter number 4, that is Economic Operation of the Power System, and this is our lecture number 3, in which we are going to study the topic number 9, unit commitment. But before we start this topic, we are just recalling the previous lecture number 2. In lecture number 2, we have discussed the topic number 6, that is penalty factor, in which we have discussed the penalty factor which is related to the the length of the transmission and the distribution from the generating station to the consumers, and as the line losses will increase, the penalty factor of the respective generating station will increase. So that we have discussed with detailed derivation, and then after we have discussed the derivation of the transmission loss formula using Cron's method, in which we have discussed it with 3 cases, and we derive the detailed equation for the power loss of the generating stations. And then after we have discussed the beta coefficient for the multi-machine power system, and in which we have detail in detail we have derived the equation for the transmission loss in power system having the two generating stations. And then after, this is our lecture number 3, in which we are going to study the topic number 9, that is unit commitment. Now, before we study the unit commitment, what is actually the unit commitment? That is the most important question. So let us discuss how this unit commitment can be done and what is actually the unit commitment is. So in the unit commitment, basically it is on the in this we can say electrical power system is say expected to have the say power instantaneously and continuously available to meet the consumer's demand, or we can say customers demand. So this is the first and foremost condition for any of the generating station that the generating station needs to fulfill the demand of the consumer by providing the pure power to the consumer or the customer. So yes, this is the basic requirement, that the power should be instantaneously and continuously available throughout the month, throughout the year, or means without any like contingency, or we can say any situation like when the fault occur, or we can say there is a power cut. It is say like it is a condition where the power is not available, but in other cases the power must be available say continuously to fulfill the customer's demand or consumer's demand. And in the say economic operations, which is depends upon the functions which are the forecasting. Load forecasting is say prediction of the load of the any of the generating unit for of the day, month, or year. And the second one is the unit commitment for the economic operation. This point should be we should consider for the economic operation of the power system or power generating station. The first point is load forecasting, the second one is unit commitment, and the third one is economic dispatch. So this is related with the transmission, and this is the security analysis. So these 4 points are most important while we are having while we are dealing with the economic operation of the power system. So yes, in which we are going to study in detail the second topic, that is unit commitment. So in the unit commitment, say it is related with the on and off of the operation of the any of the generating station or the power station to meet the load demand for the short time. Yes, this is the most important point, because unit commitment is basically associated with the uninterruptible power supply, and an overall solution of this problem which provides say continuous and reliable supply of the electricity while maintaining the optimal cost of the say production and the operation for the system. and for that we need to use say standby or we can say a set of the generating stations means which can fulfill the customers demand without power cut or without any means without any problem. So the main objective is to the unit commitment is to minimize the total production to meet the system demand. So whatever the system demand, we need to fulfill that demand, and the reserve requirement. So we require certain plant reserve means capacity for the means other reserve generating power plants to fulfill the customers demand, and to send the uninterruptible power supply to the customers. So basically the unit commitment is the most important problem in operational schedule of the electrical power generation, and generally we can say the unit commitment problem is a complex or we can say mathematical optimization problem, which is having both say integer and the continuous variable. So from that the unit commitment problem can be solved by the assigning the priority. So here what we are doing, we are having the reserve capacity of the plant, and as the see throughout the day the demand will not remain same of the customers. So yes, we are having the four types of load: the residential load, industrial load, commercial load, and the agricultural load. So all the loads having a different load demand throughout the day, and for that we draw the load curve. According to the load curve, we switch on and switch off the units for the units to fulfill the customers or we can say consumers demand. So yes, it is necessary because switching on and switching off of the generating units will save the generation cost of the say power system, because if the demand is less and plant is generating same power, and it is not transferring or we can say it is not taking part into the load shedding in the say power system, then that power will go into the waste. So yes, for that we need to switching on and switching off our units according to the consumer demand. So yes, to reach the unit commitment problem, yes, we can solve it by the assigning the priority. So we are having the number of say reserve units or we can say plants, so we can switch it on and switch it off according our requirement, and such that the most efficient unit is say loaded first. So yes, we consider that reserve generating stations or we can say additional or an auxiliary generating station means we put that stations or we can say generating units in order having say highest or we can say least say uh, highest to the least means efficiency of the power generation, and then other units are loaded according to their efficiency. So yes, we consider the most efficient power generating unit for the initial operation, and then after it will say go into the order of the say list of the frequency. Now the say from that the in the recent time the installing of the say large thermal units, say and the complexity of the power network and the other environmental pollution, again say uh, uh, need to find the better solution or approach for the determination of the economic emission unit schedule. So from that say economic emission unit commitment schedule, so from that the unit commitment problem which can be resolved by the SCUC, and say by assigning the priority for the generating unit such that the most efficient unit is to loaded first, that we already discussed. And SCUC basically determines the generating unit schedule in a utility which say for the minimizing the operating cost as satisfying the prevailing constraints such as load balance, then system spinning reserve, and the ramp rate limits and the fuel constraints. So SCUC will consider all the important parameters while we put the all the units in say a priority for the unit commitments according to their say efficiency. So it will consider these points for the most efficient power generation and the transmission, and the unit commitment basically can be solved by the finding the possible combination of the units. So yes, the unit commitment problem is related to the class of the complex combination optimization problem. So from that the unit commitment can be solved by the finding the possible combination of the unit, and then it is selected that the combination which has the least operating cost between them. So yes, this is our most important like criteria while we are dealing with the unit commitment. So we need to consider the unit which is having least operating cost while we select the priority of the units for the generation and the transmission of the power. But it requires or it consumes a lot of time in say recent time. We find out some advanced computing technological methods to solve out the unit commitment problem. So for that generally we have a certain methods. The recent time the advanced computing technology used for the unit commitment is determination techniques, and then we have the meta heuristic techniques, and the third one is say hydrothermal coordination, and the fourth one is dynamic programming method. So in this four methods generally the most important or most efficient method is dynamic programming method. So let us discuss this method in detail for the unit commitment. So in this method basically the dynamic programming method, we find out the total number of units are available. So yes, this method describes that the number of units which are available for the transmission of the power, or sorry, for the generation of the power, and their individual operating cost. So yes, this will be most efficient, this method will be most efficient because the available units, and according to these available units which are according to the generation cost. So this will be most efficient for the unit commitment for the given system, for any of the system, and which also consider the load demand on the say generating power plant. So yes, it is assumed that the load on the each generating unit, or say combination of the units which changes in certain time interval with uniform step size. So this point is important where the load is changing. So yes, as we already discussed in the previous slide, that load forecasting is most important. So load forecasting basically done by the say individual load demand, means load demand of the particular area, or for the throughout the day, or throughout the month, or throughout the year. So yes, from that yes, we can say the change in the certain time interval, what will change, the generating unit or the combination of the unit changes in certain time interval, because we need to change it, because as the demand changes, we need to change the generating units or number of generating units for the to fulfill the customer's demand. So here we are assuming that the function fn of x is given as fn of x is the maximum cost in rupees per hour of the generating say x megawatt by n number of units, and fin is the cost of the say generating of the megawatt by the nth number of unit. So fn minus 1 x minus y is say minimum cost of generating x minus y megawatt by remaining n minus 1 units. So after that the relation that we can write from detail that we have the of the function of the fnx fn of x. So that is fn of x is equal to fn of fy of n plus fn minus 1 x minus 1. This is the equation number 1 where y tends to minimum, and over here you can see that the minimum load is less than y, is less than maximum load. So yes, according to the change in load demand, we can say the value of y is varied between the minimum, we can say load means change in the load minimum to the maximum, and the load limit, say delta p maximum with say discrete step size. So what I mean by discrete step size, because as the load demand changes, we need to operate our say generating station. So yes, this discrete step size indicate that according to the particular time interval, the change in the power demand means power demand will change. So this is shown by the discrete step size, and the minimum value of the say recursive relation is say optimum value of the fn of x. So by using the recursive relation, we can easily find out the combinations of unit which requires minimum operating cost for load scheduling. So yes, from that we can easily understand that this value describes the unit which is available and which is having the good efficiency sorry, or the best efficiency for the generation. Also, uh, in the dynamic programming method, the total minimum operating cost and the load shared by each unit of the optimal, and the combinations are automatically determined for each load level. So yes, this method describes the all the units that we connect according to the load demand. And then after, if we use the dynamic programming method for two units, here we are considering two units, the most economical combinations are say n number, n is equal to 2, and which determines for all the generating stations means load by using the recursive relation. So this is the relation which describes for two units, and we can find out the maximum minimum cost of the generation, so x minus y megawatt by generating unit. By using the dynamic programming method, we obtain the most economical cost curve in a discrete form for two units. So in discrete form, if we have this cost curve, then we can switch on and switch off our units according to the requirement, and that will make our system most efficient, and we can fulfill the unit commitment demand of the of respective consumers or of the particular area. Also, it is called cost curve of the generating units. If the load demand is further increased, then the other generating units comes in the picture. So yes, initially the one unit will driving the load, and if further the demand will increase, then other generating stations which are in reserve will come into the picture, and that will serve the power. And the three combined units, considering first two units are single equivalent unit. So yes, both units are delivering power, and then after the third units will come into the picture. The process is repeated until all available units are exhausted or completely used. So yes, we are having a reserve capacity of the generating station, and this process will continuously work until the all the generating units are say live or in working, come into the working. And by using this method, we can obtain the optimal way of loading k units. So we are having the kth number of means optimal units, and by this by applying this method, we can find out the way of say loading of the each of the generators, and we can also find out the optimal loading for the kth unit. So yes, by using the dynamic programming method, we can obtain say unit commitment table which shows the unit which are in operation and require minimum operating cost for the different loads. So yes, means after applying this method, we will have a table that describe the unit commitment of particular time, or sorry, which describes the unit commitment which are in operation, means the generating stations which are in the units which are in the operation, and the required minimum operating cost for each of the generating station while they are delivering the power, and they are following the dynamic programming method for the unit commitment. And unit commitment table basically is prepared for the single time for all given set of the unit. And yes, after preparing a table, if the load changes on the say center, it will require to change the say starting and stopping time only. so it doesn't require any other exercise for the operation of the power system. And yes, it is without changing the basic unit commitment table. We do not need to change the unit commitment table. We just change the starting and stopping time of the unit which we are using units that which we are using for to fulfill the customer's demand or to fulfill the unit commitment from the generating station. And when the load is changed again, we have to find out the most economical uh, station which are having the operating cost by increasing load in say uniform step size. So this is the most important point. If the further load will increase, then we need to find out the most economical station which are operating cost by increasing the load in say uniform step size. And by changing the value of the number of generating units n, find the new recursive stations between the generating units. So this process will go means repeatedly move ahead, and we can find out the say most efficient unit of the generating of the generating system, and that will deliver the power. So yes, this process actually done without shutting down the system. So yes, the customers or consumers will get the uninterruptible power having a good unit commitment. So this is the policy that all the generating stations should keep for the uninterruptible power to the customers or consumers uh, to fulfill the unit commitment. Now let us discuss the example which are based on this chapter. So let's start with the example number 1, that is the fuel cost of the two unit plants are given by the C1 is 160 plus 4 P1 plus 4 0.008 P1 square, and C2 is 250 plus 4 P2 plus 0.02 P2 square, where P1 and P2 are in megawatt. So this is the generation of the particular plant, and plant supplies a load of 600 megawatt. So P1 and P2 both are combined and both are power delivering the power of 60 megawatt. So find out the economical load scheduling of two units and the incremental fuel cost. And here the one point is given, that is neglect the losses. So yes, let us discuss the solution for the given system. So first of all, the incremental fuel cost, that we have the equation IC1 for the C1 is we are doing the differentiation of the C1 respect to P1. So yes, for the P1 that will be the 4 plus P1 will be 1, then plus 2 is come over the here, and 2 into 0.08 P1. So the solution is 4 plus 0.016 P1, and it is rupees per megawatt hour. So this is the equation number 1 for IC1. Similarly for IC2, the incremental fuel cost of the second generator. So we are differentiating this IC2 with respect to P2. So yes, over here P2 is over here. So 4 plus 0.02 into 2 into P2, so that will be 4 plus 0.04 P2 rupees per megawatt hour. So this is the equation number 2. Now for optimal load say division, the two incremental costs should be equal. That is the necessary condition. So if two incremental costs are equal, then we can equate the IC1 is equal to IC2. Now put the values of IC1 and IC2 that we get through the incremental fuel cost derivation of IC1 and IC2. So it is 4 plus 0.016 P1 is equal to 4 plus 0.04 P2. So yes, from that we can write P2 is equal to 0.4 P1. And one more thing, the plant is supplying the 600 megawatt, so we can write P1 plus P2 is equal to 600. So let us write that the total load is shared by the two generators. So P1 plus P2 is equal to 600, and we are substituting the value of P2 from the 4.39 in equation 4.40. So 4.39 is here, so P2 is equal to this. We are putting this value over here. So P1 is equal to 0.04 P1 is equal to 600. So P1 will be 428 128.57 megawatt, and by putting this value in this equation we'll get the P2 is equal to 0.4 into 428.57, that will be 171.43 megawatt. So these are the power which is generated by the P1 and P2, and the incremental fuel cost of generator 1 corresponding to the P1. Now let us consider this P1, and let us describe the P1 over here. So IC1 will be 4 plus 0.016, and P1 is that we have find, that is 428.57, so we are putting over here. So IC1 will be 10.86 rupees per megawatt hour, and in this you can see that the cost, that is the 4 plus 0.016 P1. So we place the value of P1 over here, that we have find through this equation. Now the incremental fuel cost for the generator 2 corresponding to the load P2 is equal to 171.43, that we have find out from this P2. So yes, that is IC2 is equal to 4 plus 0.04 into P2, putting the value of P2 over here 171.43. so the incremental fuel cost for the generator number 2 is 10.86 rupees per milliwatt, for megawatt hour. So hence the incremental fuel cost of the plant for most economical operation is 10.86 per megawatt for both the generating stations. So this is how you can calculate the example related to the incremental cost. So let us discuss the next example, so that will be more elaborating for you to solve the examples related to this. So in this example, simple power system consists of two power plants over here. Plant 1 is over here, plant 2 is over here, which are connected with the bus, and this is the transmission line, and this is the bus which is delivering power to this load. Now a transmission line and the load in the system is directly connected in the bus at bus of the plant 2, so it is indicated over here. When the 100 megawatt power flows from plant 1 is transferring 100 megawatt to the plant 2, and then 15 megawatt is lost in transmission line. The incremental cost of the power plants are DC1 by DP1 is equal to 0.20 P1 plus 22 rupees per megawatt hour, and DC2 by DP2 is equal to 0.15 P2 plus 30 rupees per megawatt hour. So calculate the economic loading of plant 1 and 2 for the system, and where the lambda multiplier is equal to 60, and you can also calculate the transmission loss and the total loss demand. So let us find out the solution of this. The solution is given as this is the given in the data, that is two plants. So these are the plants which are connected with this line. So let us discuss the solution. So in transmission loss, generally we have the equation that is we have already derived, that is PL is equal to B11 P1 square plus 2 B12 P1 into P2 plus B22 P2 square. So this is the equation that we have derived from the loss for transmission loss formula. So since the load is at the bus 2 of the plant at the bus of the plant 2, therefore the loss is depending on the P1 only. So because at the P2 means there are no long distance for the transmission compared to the P1, so that's why we are considering P1 over here, and P2 we are not considering over. Therefore B12 is equal to 0 is equal to B22, because we have considered the B12, this is this is the point where we are P2 is connected over here, this is P2 is connected over here. So this is B12 is equal to B22, we have considered this point as we have P2 is over here, that's why B12 is equal to 0 is equal to B22. Now substituting this in equation 4.49, the PL is equal to B11 P1 square. So given that P1 is equal to 100 megawatt and the PL is equal to 15 megawatt, the loss that is given in the data. So substituting this in equation number 4.50, so 15 is equal to B11 into 100 square. So B11 will be 0.0015 megawatt inverse. So that we have already discussed why we will get this value in megawatt inverse. in the theory section. Now substituting this value b11 in equation 4.50, so we are putting this value in 4.50 over here. So PL is equal to 0.0015 p1 square. So now we are taking the differentiation of this term in terms of p1. So yes, del p1 is equal to del p1 by pl by del p1 is equal to 0.003 p1, and the del pl by del p2 is equal to 0, because p2 is not over here, so it is 0. And for economic loading of the plant output must satisfy from the equation 4.51, 4.52 and 4.53, that we have all the conditions. And it is given that the multiplier lambda for the economic output. So yes, it is 1 upon 1 minus 0.03 dc1 by dp1 is equal to 60. We have just make the subject over here, so that will be 1 by 1 dc2 by dp2 is equal to 60. Now substituting the value of dc1 by dp1 in equation 4.54. So yes, by putting this value, that is 0.20 p1 plus plus 22 divided by 1 minus 0.03 p1 is equal to 60. So after solving this, the p1 will be the 38 by 0.38, so that means it is 100 megawatt. So by substituting the value of dc2 and dp2 in equation 4.55, will get the equation that we have already, that is 0.15 p2 plus 30 is equal to 60. Over here p2, we are finding the p2 is the 30 by 0.15, so that is 200 megawatt. So substituting the values of p1 in equation 4.51, so pl is equal to 0.015 into 100 square, so that will be 15 megawatt. So and the load demand, that is PD is equal to P1 plus P2 minus PL is equal to 100 plus 200 minus 15, so that is 285. So total load demand of this particular system is 285 megawatt to deliver the power, or we can say committed power to the consumer, which are connected with the load. Now let us discuss the third example related to this type of topic. So for the system, the voltage at bus C is VC is equal to 1.0 at angle 0 pu, and the current in the lines AC and BC are the 1.05 at angle 0 and 0.9 at angle 0 pu respectively. So this is AC and this is for BC, and the line impedances are as follows. So ZAC, ZBC and ZCD all are the impedances which are mentioned in the data. And find the loss coefficient and the transmission loss. The solution which is given as, we have this equation, VA is equal to VC plus ZAC into I1. So by putting this values, we will have the solution, that is 1.0525 plus J 0.21 pu. So this is the equation like VA cos phi A plus J VA sin phi A. So yes, VA cos phi A is equal to 1.052. From this equation you can see that VA cos phi A is equal to 1.052. So and VB is equal to VC plus ZBCI2. This is the equation. After putting all the values, we can have the solution, that is 1.036 plus J 0.144 pu, and in this VB cos phi B is equal to 1.036. So yes, we are comparing this two, so we can find out the solution over here. Now plant 1 having the power output, that is P1 is equal to I square R. So RE is the of the means resistance, and the VA into I1 conjugate. So this is the equation of P1, in which we are putting the value of VA I1 conjugate over here. So the P1 will be the 1.0105 pu, and power output of the plant number 2, so P2 is equal to RE VB I2 conjugate. So RE into the VB that we have already derived, or we can say by it is given, and multiply with the 0.9 at angle 0. So the P2 will be 0.9324 pu. So from that, the B11 equation is RAC plus RCD divided by VA cos phi A square. These are the equation that you need to remember for the solution of such examples. So by putting these values of RAC, RCD, VA, cos QA is after that B11 will be 0.072218 pu, and B12 will be after putting all the values, there will be 0.027513 pu, and B22 will be the 0.065296 pu. So the transmission loss equation that we have, PL is equal to P1 square B11 in plus P2 square B22 plus 2 P1 P2 B12. We have all the values. After putting these values in this, the PL will be 0.2015944 pu. So after that, you have the assignment question is explain what is unit commitment. Also define the dynamic programming method for the unit commitment with suitable derivation. The related instructions which are written below, please read it carefully. If you have any query or any doubt in this topic or in this presentation, we can solve your queries and doubt in our doubt solving session. If any query means further query arise after watching the presentation, feel free to call me to solve your doubts related to this topic as well as the electrical engineering topics. So thank you very much, student. Thank you very much all. Jai Swaminarayan.